Okay, first of all, we're going to go through the do now for today, and that's on page 591, number 56. And in this particular situation, we're given a case of equilibrium. Now, this is the value. This is not the expression. Okay, it's a given value, and you notice it has no units of measure. So, as we go down here, we see that we've also been given the balanced equation. And this is where A is some substance and B is a different substance, and they're coming together to form substance C. And when we balance it out, we got two of these guys and one of each of the others. So balanced equation is required for us to be able to do an equilibrium expression. Now the equilibrium expression, which is in the find, we have to use this to be able to create. Okay, so we're also given a table that has all of this information in it. I don't care if you copy this part down. All right. So under find, we're supposed to, first of all, to be able to do what they're asking us to do, we have to find the case of equilibrium expression. Now this guy is very similar to what you're going to see in a little example that I'll give you, if I can find it. I got it here? Yeah, there it is. Okay. We'll go over to the Elmo, and this dude right here is a specific equation. This is the Haber process for making ammonia, and this guy down here is the expression for this balanced equation. So reactants on the bottom, product on the top, and we got a done deal. The 2 here as coefficient becomes the exponent here, and the 3 here is the coefficient for hydrogen and becomes the exponent down here. This is the expression. That's what I'm talking about with expression. So let's go back and continue. So we've got to find the equilibrium expression, so we know what that means now. And for right here, we're supposed to find the value of case of equilibrium for the first and the second set of conditions. Now look at these guys. They're all over the place. These have no seeming relationship to this at all. I'm going to show you how they both have an exact, specific relationship. To both sets of numbers are going to be related by one thing, and that's going to be this K equilibrium expression will wind up giving us the same values for the K equilibrium, the actual value. So that's what they were actually asking us to find. Are solutions A and B both at equilibrium? Okay, the first is A and the second is B. First, second. All right, now as we go down here, the first thing we have to have is the expression, correct? Okay, so when we move this guy out of the way, we can see what the expression is. And now, as we go further into this, let's see if we can figure out the rest. Look! Can you see where the 700 came from? See, the 700 is this guy right here, letter C in the first guy, and he is a product here in the equation, so that's why he's on the top. And so we fill in C with 0.700, we fill in B with 0.62. Well, I've got these guys reversed. They shouldn't be reversed. But anyway, B's over here. It really doesn't matter, but B is squared, so I've got that right. And then we've got 5 for letter A. And when you square this and then work the numbers, you wind up with 3.63. Isn't that interesting? That's how this set of numbers relates to the case of equilibrium. So we would say, what do you think? Are these guys at equilibrium? Yeah, they are. And the reason they're at equilibrium, and we know they're at equilibrium, is because this number and this number are equal. Am I making sense? I hope. Okay, let's get rid of this now and look at the second set of numbers. Okay, we put in our numbers, and we have the 0.250 is this, letter C. Where you come back from the field trip? Yeah, okay. That's fine. That's fine. Thank you. And so this guy is up here for letter C. A and B are down here. And here's our A and here's our B. So we've got this guy licked now. And you see I reversed it from here. Are these able to move? No, they don't move. Okay, so I can't do anything about that. But at any rate, we've got the B is squared. And let's get this. Come on. Come on. I know you moved. Here. Is this all together? Ah, that's how it moved. Okay, I'm trying to line up my decimal points here. So, at any rate, this guy also works out to 3.63. And that's how these two sets of numbers are related. They are both solutions at equilibrium. Solutions of the same three elements, are the same three, compounds and elements. So, the answer, very nice. We are at equilibrium with both of them. And you're going to see how equilibrium constants change, or not constants, but expressions. The value, how the k-equilibrium things are going to change, how all of these concentrations will change, but the equilibrium constant, which is gotten by plugging these numbers in, will wind up being the same, even though they change. All right, let's move on. This you need to copy down. Get it all. Every single thing that's on that page. Yeah, well, this is actually... Now, what we're going to do is watch an animation, and I'm going to be describing what happens in each animation. But first of all, we want to understand what it is that we're really watching. And you're going to be seeing... You notice you have this now on your paper? You have this on your paper, and that's under concentration, and you'll notice that everything here is labeled as AQ. Did you get the AQs in there? That's important. Changes in concentration. When you have an aqueous solution, you're always going to be dealing with changes in concentration. That's what's going to happen with aqueous solutions. Anybody not familiar with aqueous? Dissolved in water. Okay? So what we're going to do is we're going to add sodium thiocyanate, cyanide, and then we're going to take another stress. By the way, these guys are considered stressors. We're going to add or take things out. And these little dudes are referred to as species. Species. Yeah, why they have to do that, I don't know. But anyway, that's the name for the individual parts of the equation. That's all. Not a biggie. Don't be scared off by that term. It just doesn't. It's not that scary a deal. And you'll notice here that I took these colors and I put them underneath these dudes, the species, so you know what color each species is. And you're going to see a lot going on when we do these animations, which is why I'm doing this outside of the animation. I took screenshots and put them in here so we could talk about this without all this stuff moving around. This window right here is what we call the nano world. That means that there's 9 zeros. In other words, this is magnified 1 billion times to be able to see it the way it is. This is little stuff. That's why you can't see it when it's in the water. When you throw salt into the water, you can see it until it dissolves. What happens when what happened to make it dissolve was that it had to separate into individual atoms. And you have to magnify them 1 billion times to be able to see them. That's why the water looks like there's nothing in there. When you taste it, it's salty. You bet it is. You know something's in there. There's lots of ways to test it to see that something's in there. But at any rate, this is what we're looking at. And then next, this dude is kind of a single of the concentration part of the notes that you just took, okay? And this applies to this screen. Notice I have them both in blue. So, this dude was colorless, this guy's pale yellow, and this guy is red. And the shifts to same and opposite, these are the terms. Did you underline these guys in your notes? Yeah, these are the terms that you're going to use in the chart that I gave you in class today, which of course looks like this. Okay. And you're going to put your name, date, and period at the top, and then you're going to put the page number for the problems that you're working on and the problem letter, and then we'll talk about stress, what LeChat does, or what LeChat wants, and what he is going to wind up doing to achieve that goal. And finally, we'll figure out what the shift is in the equation when you stress it. And that's all wild. This is crazy stuff. It takes a little while to get used to it. And this is where we're going to work a problem or two based on this equation here on a sheet that's right after it, after we look at the animation. So let's continue here. Changes in pressure. Changes in pressure. In fact, why don't we do the animation as we go? So now that we've talked about changes in concentration, let's actually see the animation and how that actually works. Here we go. Yes. And I'm at school here, I'm turning off the lights so this is a little bit easier to see, because colors are very, very important. Now, NaSCN is what we call the thing that causes the stress. And because this guy is a compound, it's actually made up of this sodium 1+. Ooh, this guy is not in line. Okay, 1+, and then we're going to have the SCN 1-. Those are the two species. Well, this guy may as well not even be there, because he is not in here, he's not here, he's not here. He's not any of those species, so he doesn't affect the equilibrium. Isn't that interesting? Has no effect on the equilibrium. So let's go ahead and clear this. Yeah. And let's go ahead and add him and see what he does. What's your expectation? If just think of it as plain SCN. What's that going to do to this bar? Huh? What's it going to do? Huh? It is going to do something. Is it going to go up or down? You bet it's going to go up. And when it goes up, LeChatelier, I refer to him as LeChat. Okay, we just abbreviate that. It's easier to say. And LeChat is like a naughty teenager. Now, I know that nobody in this class has ever done this, but Dad says, all right, my dear, you are never going to see that young man again. I don't like him. I don't like his friends. I don't like him as a friend to you. Just off limits to you from now on. And you do one of two things, right? You say, too bad, I'm going to see him anyway. Nah! And you stomp out and you slam the door to your room. And you cry and you bellow. And, oh, Daddy, please. You know, anything to get him turned around. You know, you girls, you have an unfair advantage with fathers. Yeah. Anyway, so that you either do that or you say, yes, Daddy, and you smile at him and move your head up and down. And then when he's not around, you're sneaking out and getting to see your boyfriend. Yes. So that's a naughty teenager, right? And I know none of you are anything like that. Never do anything of that nature. So, at any rate, so LeChat, if we make this bar go up, LeChat is going to try to push it down. In other words, he wants to get rid of that stuff. Now, how can he do that? Any ideas? Now, the stress is that we're going to add it. We're going to add this stuff. Okay? So if we add this stuff, that's the stress. What does LeChat want to do? He wants to push it back down, but how can he do that? How can he get rid of this? He can't take anything out. He can't put anything into this beaker. He's got to work with what's there. If the reaction goes this way, what's that going to do to the concentration of SCN? I break up these guys, iron and SCN. I break them up. That's this reaction, going to the right. What happens when I go to the left? These two get together, and we have this guy, and each pair of these that get together takes out one of these guys and takes out one of these guys because they're no longer there. This is a whole new thing. So that's going to be a shift to the left. And you'll see how those guys work in just a minute. But first of all, let's witness how it goes down. Here we go. See? There's the stress. Now here comes LeChatelier. Ooh. Who went down and who went up?
Red went up.
Red went up.
Yellow went down.
Yellow went down. And?
SCN.
And the SCN went down. Okay. So these two went down. What does that mean? What does going down mean? Huh? No. What does it mean when these go down? And they both went down together. That means this is happening. These two get together and form this. That's what LeChat encourages, you see? And going the other way, we take this guy, break him up, and we can make more of this. But it also makes more of this, because every one of these that I break up creates one of these and one of these, right? That's what the coefficients tell us. The ratio in the balanced equation is 1, 1, 1, right? All the coefficients are 1. All right, watch this again. See if you can catch it. Now, I don't think everybody saw it. I know when I first looked at this, I didn't see everything that was going on. Let's try it again. Okay, here we go. Here's the stress. Bang. Okay, up that goes. Now, look, that's down, and I guess we're done. Do it again. Okay, watch this guy now. Watch him. See, he's going up. This guy's going down.
Oh, the yellow and the one.
Yeah, the yellow one went down as well because both of these guys are disappearing because they're making this. That making sense now? Okay, good. Let's go ahead and go back to the little screen that we had here, and let's deal with this guy, FeSCN, and he's going to make iron and thiocyanide. So I'm going to draw that up here at the screen on the other side, and whoops, not here. Here. Okay, this is FeSCN, so we can see what it is. FeSCN, and this is going back and forth, and we're going to get iron Fe3+, which is what color?
Yellow.
SCN 1 minus. This guy right here is colorless. This guy is yellow, pale yellow, and this guy is the red or brown, is it? Red? Yeah, okay, thank you. I can't tell the difference. Alright, now, here we go. This is this is animation. Okay, animation 1. And the stress, I'm gonna do several different stresses. Okay, first of all, we will add FE. So FE, the way we're going to write it here, when we add FE, the iron 3. Now you want to do this on the back of your paper. Everyone, back of your paper, you want to copy this down because you're gonna learn how this stuff works by doing it. So the way we say that did I say add or take away? Add. Okay, well, if we're going to add him, his concentration goes up, right? So just an up arrow is fine. I'm making this as simple as I know how to make it. Okay, what does LeChat want to do? Fe3 plus, he wants to get it down. Okay, so what is he going to do? Is he going to move to the same side or the opposite side of the balanced equation? Which way is he going to shift? Or first of all, where is the Fe3? Right side. Okay? So if he wants to make less, if he wants to take it away, he's got to go to the opposite side. Can you see what? Opposite. Opposite to what? Opposite to this guy. So put your finger on this and say, what's the opposite of this side? This side is right. Opposite is? Left. Left. So the shift is left. Okay. I added iron. Let's concentrate on SCN now. Let's get rid of this guy and put him back. And now let's go on the SCN. This guy, I put him up. Let's take this guy and put him down. Okay, so this is going to be SCN down, and he's a 1 minus. And what does LeChat want to do? Yeah, he wants to put him up. He wants more. SCN 1 minus. So he's going to increase. How in the world does he do it? Same or opposite? He needs to make more. More means we go to the same side. Look at your notes. I put that all in there. More means we go to the same side. And the same side is?
Right.
Right.
That's the 1 minus, right? For the first one?
Yeah, the SCN is a 1 minus. He's always a 1 minus. Yes.
Yeah, it's kind of
Yes. Okay, and so this time the shift is to the right. Because that's the side that the SCN is on, and we're trying to increase it. Okay? Let's try again. Fe SCN now. And this guy is an ion. Oh, what is the charge on that dude? It's got to be a 2 plus. Yes, 2 plus. Okay, and this time let's add some in. And this is what we actually saw in the animation, isn't it? So we're going to add some, and that means LeChat that wants to do what?
Go down.
He wants to go down, you bet. And now, what is he going to do to get the SCN now down? Ah, he's going to go opposite. So if we look at SCN, and I recommend literally putting your finger on the paper where the SCN is so you don't get mixed up. It's so easy to get mixed up with this stuff. I'll tell you, you need every little help you can get to get them right all the time, especially since it's new to you. So I've got my finger on the left side, so the opposite is going to be the right. Are we good? Is this starting to make a little sense to you? Okay. This is how you deal with these guys, and we'll do some more. We're going to do another one now. Okay, so we're going to do this animation, and this guy, I would write him as I with the lines above and below, the horizontal lines, so you don't confuse this with what? 1 or L, yeah, right, L, yeah, any of that stuff. This will keep you from doing that. So, this animation deals with gases instead of liquid. And to do gases, we have to do a situation where the pressure is going to change with a piston. This piston is going to shove down or go up. When we shove it down, what's it going to do to the pressure?
Increase.
Pressure is going to increase. It will. And when we go up, the pressure will decrease. Okay, so putting it down increases the volume, doesn't it? Or decreases the volume. So when we decrease the volume, we increase the pressure. It is an inverse relationship. And inverse relationships are like this. One goes up, the other goes down, right? Yep. Okay. Let's get rid of those. And now, when we look at what we're going to be doing, we're going to stress it by increasing the pressure. We do that by changing the size of the vessel, is the way you'll read it in a lot of your questions. So if we change the size of the vessel, we're changing the pressure at the same time. So let's go ahead, and this was the guy that you copied down that dealt with this. And you'll notice what I'm saying now. These are going to start to make sense to you. Shift to the side with more moles. How is this different than what we did before? Huh? What did we do before? Here, let's go back. What did we do before? Here, same or opposite side as the species we're talking about, right? Notice same and opposite come in with temperature changes that are stressing this situation. But this guy is more moles or fewer moles. That's how LeChat takes care of pressure changes. He doesn't really take care of it, but he gets it back that direction. So we're trying to talk about here what happens with pressure changes. So let's go back to the animation now. And let's look at pressure changes. Oops. Yeah, pressure changes. Okay, here we go. Pressure changes. Now, that's with the piston. And increased pressure, we know that the piston's going to go down. Now, let's watch what happens here. And first of all, let's look at this. Notice there's a coefficient of 2 here. That's what we mean by more or less moles. Think of the coefficients now as mole ratios again. We did that before, right? Think of it as mole ratios, and this would be moles. So a mole of I is the same as a mole of I2 so far as the pressure it will exert, or the pressure it will make. So, where do I have fewer moles? I'm going to increase the pressure, I've got to decrease it. And I'm going to do that by decreasing the moles. Which side has fewer moles? Hello? Anybody out there? Leslie? Huh? Oh. Art's absent. And Vince, how about it? Which side has fewer moles? The left side. All right, let's see if you got this right. I'm going to increase the pressure. Here we go. And there we go. You see this guy went down, and this looks a little darker, but watch what's going to happen up here. How many of the purple dudes are in here? 4. Because they're doubles, okay? Oh, now what do we have? 6? Yeah, we added 2, and look what happened to the amount of I. The I went down, and the I2 went up, which is exactly what we were hoping to see. Okay, so that cuts the pressure almost in half by doing that. That's pretty good. So he can get a long way with that. Now, let's go ahead and see how this works out. I'm going to write the equation again, and we got I2 on one side, I sub 2 on one side, and we're going back and forth with I, which is got a coefficient of 2. Alright, so here's the stress. And this is the animation again. ANIM, I'm going to abbreviate. And we're doing the pressure. Okay, so let's raise pressure. So we're going to put pressure up. And LeChat wants to do what? Come on, what's LeChat want to do?
Go down.
He's a naughty teenager, okay? He's going to do that. Pressure.
What do you mean he's not a teenager?
I explained that earlier.
Oh.
Not now. Okay, so LeChat is going to want to put it down. How does he get down? Which side is got, if he's got to go down, he needs fewer moles, right? Fewer moles. And this one is really easy to tell because all you have to do is look at the total number of moles on each side. It gets a little more difficult when you have 3 or 4 reactants and products. Okay? But here it's real easy. Which side has fewer?
The left one.
Yeah, the left guy. Okay, so he's going to shift left. Left. I got that right? Yeah. Okay. All right. This time, let's do pressure down. Because I can only try 2 different things now. What is LeChat going to do? Or try to do? What does he want to do? He wants to raise it. Okay. And what side does he have to go to? Okay. And why are we going right? How's he doing it? More moles. Okay, more moles. And to get more moles, he has to shift to the right. See, this is going to go pretty fast for homework, isn't it? Yeah, really will. Okay, let's do the last situation where we have gases again, only this time we're going to be dealing with temperature. Okay, and that screen's going to look like this. And the 2 species that are involved in this are going to be the N2O4 and the NO2. So let's go ahead and jump right into it. You can see what's going to happen. We're going to have a colorless and a brown. And let's watch it happen. And that has to do with this stuff, right? So shift to the same side as the heat. Oh! Okay. This guy is called exothermic. Not exo. No, this is endo. Endo's on the left. Endo. This is an endothermic reaction. It's endothermic because heat's on the left.
Exothermic is to the right?
Yes, very good conclusion. And exothermic means that the heat will be on the right-hand side. And that's important for us to decide, or to help us decide, which way LeChat's going to move. Okay, when we do our stress. Okay, so let's go to the animation and see how that works. Here we go. We're going to go back here. All right. Well, we've already done this guy. We wanted to do the the temperature one, and that's going to be here. All right, I'm going to increase the temperature, and look at this. This is so darling. Aw, look at that. Isn't that cute?
The flame heats it up, right?
Flame heats it up. Now, we got to watch what's happening here.
The bar goes up.
Oh, whoa. Hey, that popped up, didn't it, huh?
It's brown.
Okay, it's brown, yes. And the brown has increased. So, let's talk it through. Why is it shift right? We added heat, and so LeChat wants to get rid of it. And what is the same and opposite? Same side as what?
Decrease.
Same side, opposite side of what? Same or opposite to what thing? Heat. Yeah. So, if we increase the heat like we just did, we get rid of it by going to the opposite.
So when it goes to the left,
When we want to get rid of heat, we go to the right. So, when we decrease the temperature, look, isn't that cute? Nice bath. Oh, it's so darling. All right. And as it decreases the temperature, we would expect this guy to go up, yes? Yeah, and that's exactly what happens. That's a shift left, and that means that we are going to the same side as the heat to get heat. Okay? Okay, let's make this thing happen. Let's see how we work with this particular equation. The N2O4 dinitrogen tetroxide to nitrogen dioxide. And so LeChat, we're going to take the first one right up here. So if we stress the system by adding heat, LeChat, of course, wants to take the heat down. Now to take the heat down, he has to go opposite, and he goes opposite to where the heat is. Now the heat is sitting right here. He's on the left side. So opposite of the left is right, and that's the direction of the shift. This is probably going to get a little easier for you each one we do. We're going to do this guy now, and when the heat is down, of course, we want the heat to go back up. That is, LeChat wants it to go back up. And because heat is on the left, we have to go same to increase heat. And same, in this case, is on the left. And so our shift is going to be a left shift. The more of these I do, the easier it will get for you. All right, pressure. Pressure up, pressure down. You see, this particular equation, anytime we're dealing with gases, we could deal with heat or pressure. And so pressure up, LeChat wants to put it down. And now we have to go with the mole idea. Which side of this equation, let's see, we want to go to take the pressure down, we've got to go to the side with fewer moles. Now you can see we have a coefficient of 1 over here, and we have a coefficient of 2 over here, and I'm pointing to this guy and this guy. Okay, so if we're trying to get to the side with fewer moles, the fewer moles is going to be over here, and that means that we're going to have to go to the same side, or to the side with fewer moles. The side with fewer moles is the left side. And if we want to go to the next problem now, this guy has the pressure going down, and let's take the pressure up. And the pressure to go up has to go to the side with more moles. And the side with more moles, of course, is over here, because 2 is larger than 1. And so that makes that a shift to the right. And that's it. I hope this is going to be a big help to you. LeChatelier can be very confusing, but with this chart, it should be relatively easy for you. That's it, folks. Have a nice weekend.